So the basic thing is that the probability of an outcome being in a set A is the sum of the probabilities, Pj, of all the different mutually exclusive outcomes, J, in the set A. So that's this description there. Let me move this to another part of the screen, and I'm going to make this bigger. So this is intuitively what we mean by probability. You add up the individual probabilities, and that's the probability of the whole set. So if you have dice, the probability that the sum is 2 is, if you throw 2 dice, then the probability is only one way of it happening, namely that you throw, that you get the number 1 twice, so that's 1/6, and that means it's 1 over 36. Probably the sum is 3. Well, it's P12 plus P21. That's 1 over 18. Anyway, the set of all possible outcomes is called the sample space, and any subset of the sample space is called an event. I'm giving you the sort of standard terminology here. If A and B are 2 sets of outcomes, of course, in ordinary language, we call outcomes events or results. The probability of an outcome being in the union is the sum of the probabilities minus the probability of the intersection. So the probability of an outcome being in either set A or set B or both is probability of it being in set A plus the probability of it being set B minus the probability of it being in both. And if the outcomes are mutually exclusive, then P of A intersection B is 0, and the probability of the union is just P of A plus P of B. The joint probability, P of A comma B, is the probability of the intersection of the 2 sets. And if the joint probability is the product of the 2 probabilities, then we say the sets are statistically independent. So these are just basic definitions. Now, the probability that a result or an outcome in set B also is in set A is the conditional probability, P of A given B. And that is, P of A given B is the probability of the intersection divided by the probability of B. And of course, the reason for that is the probability of the intersection is the probability of 1 times the probability of the other given the 1. If you interchange A and B, then you get that the probability, A and B are obviously symmetrical in this expression. So if you interchange them, you get probability of B given A is the probability of B and A divided by the probability of A. And since these 2 sets are identical, you can write the probability intersection this way or that way. Either way, it's probability of B given A times probability of A, and it's also equal to the probability of A given B times the probability of B. Now, this last equality is Baze's theorem, and that's that the probability of A given B is this thing divided by probability of B. So the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. And this, this relation leads to some amusing and surprising results, but it's in fact true. And the interesting thing is it was discovered by I think a member of the English clergy back in the early 18th century. So some of the lingo in the trade, lingo that I don't really use, is that the probability of A given B is the posterior distribution of the observable A given the B data, while P of A is the prior distribution of A before the B data became available. Well, that's some of the lingo. The probability B given A of the B data given the observable A is the likelihood of the data B given A, or of the B data given A. If a set of outcomes is contained in a union of n sets AJ, I think that should be the union of n sets AG that are mutually exclusive, then we sum over them. So the probability B is the probability B given AJ times the probability of AJ summed over AJ, assuming the AJs are all mutually exclusive. And so an example here is AJ might be the probability. No, AJ isn't a probability. AJ is I'm writing a note to myself to fix this. If AJ were the selection of an atom with ZJ protons and NJ neutrons, then the probability, and if probability B given AJ with the probability that such a nucleus would decay in time t, then the probability that the nucleus of a selected atom with decay in time t would be given by a sum like this over different kinds of atoms. In this case, if we replace A by AK in the earlier formula, which is the one that led to Baze's theorem, then we get the probability of B and AK is the probability of B given AK times the probability of AK, and it's also the probability of AK given B times the probability of B. And so if you combine this with 15.8, you get that the probability of AK given B is the probability of B given AK times the probability of AK. Now we have to divide by the probability of B. The probability of B now is the sum over these non-exclusive, over these disjoint sets AJ and their probabilities, and the probability of B given each of them. And if you sort of rewrite this whole thing, in fact, if you just invert this formula, you get this formula. So let me give an example of this. This is an example I found in a book by someone named Kahneman, who I think won the Nobel Prize in economics, actually. I'm not sure. Anyway, was the cab blue? So, and this I think is an example that should be taught in law school. Of course, most law students couldn't follow it, so never mind that. All right, a cab was involved in a hit and run accident at night. In this city, 85% of the cabs are green, 15% are blue. Here, let me just write it down. Another note. A witness said the cab was blue. Tests showed that the witness correctly distinguished green and blue cabs only 80% of the time. What is the probability that the guilty cab was blue? Okay. So we go through this first by making quantitative the statements here of the problem. So the probability of a random cabs being blue is 0.15. That was what was set up here. The probability of random cabs being green then is 0.85. The probability that the witness would call a blue or a green cab blue are probability witness blue given blue 0.8 and probability witness blue green 0.2 because she'd call or he'd call, I don't know why I thought it was a woman, bad. Well, anyway, so the witness, he or she, well, anyway, whoever it was, the probability that the witness would call it blue if it was green was 0.2 because the witness called 80% of the cabs, called the cabs correctly only 80% of the time. So she'd get a green cab wrong 20%. He'd get a green cab wrong 20% of the time. So the probability that the witness would call a random cab, that a random cab would say that a random cab was blue is probability it was blue times the probability the witness would say it's blue given that it's blue, probably it's green, probably the witness would say it's blue given that it's green. So we've got all those numbers and we add them up and we get 0.29. Now, Baze's theorem gives the probability that the cab the witness said was blue actually was blue and gives it as PB given the witness said it was blue as the probability the witness said it was blue given that it was blue times the probability blue divided by the probability that the witness said it was blue. Well, we know that's 0.29. The probability the witness would call a blue cab blue is 0.8, and the probability of blue is 0.15. You multiply them together, you get 0.41. And that's half the naive answer. So in other words, in as much as 80% of the cabs are blue, the naive answer, which is the probability that the guilty cab was blue, that is, instead of being 80%, it's actually only 41%. Okay, here's another example, and this is relevant in medicine, and it's relevant. It's not so relevant now because this COVID thing is a very common disease. But suppose you had a rare disease in a population, and of course, fortunately, many diseases are rare. And suppose you had a test for the disease that had a sensitivity of 99%. That is, the probability that a carrier of the disease will test positive is 0.99. And suppose this test is really a good test in that it's highly selective. And that is that it has a false positive rate of only 0.005, half of 1%. So the probability of the test saying the person's infected or has the disease, given that the person is not infected, is only half of 1%. And the probability that a random person in the population would test positive, is probability positive given disease times probability of disease plus probability positive not diseased given not diseased. Well, if we put those numbers together that we already have, we have this one, we have that one, and then we have this one and this one, probability n just being 0.999 actually. And you multiply them together and you get something like 0.006. So now Baze's theorem tells us that the probability that a person who tests positive actually has the disease is only, it's given by Bayes' formula as being that. And so that's probability positive giving the disease, that's that it's a really good test. Probability of the disease, it's a rare disease. And then the probability that a random person has the disease. No, the probability that a random person would test positive is this, and you work it out and you get 0.165. So this is a very high false, this means that the test, because the disease is so rare, even though the test is very good, it doesn't do a very good job, because the probability that a person is diseased, given that the person is gets a positive test result, it's only 0.165. And the probability of a person testing positive actually is healthy is 0.83. So in other words, you've got a false positive rate of something like almost 84%. So what this means is that if you have a test, then screening for rare diseases doesn't work very well. It's also true that screening for rare behaviors is also dicey, even with a good test. And it's absurd if you have a poor test like a polygraph. So now let's go to the three-door problem. This is an amusing problem, and preparing for class, I read through it and was once again amazed. I don't know, maybe some of you are so perceptive that the three-door problem that the result of the three-door problem strikes you as perfectly natural. I find it quite bizarre. By the way, let me just interject here. We're talking about classical probability theory for a world in which there's no quantum mechanics. So this is probability in the sense of classical probability theory. I'll have something to say about quantum mechanics in a moment. So here we have a prize lying behind one of three closed doors. Contestant gets to pick which door to open. And before the chosen door is open, the moderator says, okay, stop. And a door that does not lead to the prize and was not picked by the contestant swings open. So should the contestant switch and choose a different door? And so here's the analysis. And once one goes through the analysis, one finds that one ought to switch, and one does twice as well if one switches. So let's go through the probability theory. A contestant who picks the wrong door and switches always wins. So probability of winning, given that the person picks the wrong door and switches, 1. Because there are only 3 doors, and one is open, and one is the one picked, and then there's the other door. Okay. And so if the person picks the wrong door, then switching is obviously right. While one who picks the right door and switches never wins. So that probability is 0. Now the probability of picking the wrong door is 2/3. So the probability of winning if one switches is probability winning given that you switch is probability wrong door times probability of winning given that you switch and pick the wrong door, plus probability of winning given that you switched and pick the right door times the probability of the right door. Well, this thing is 0. This thing is 2/3, and this is 1. So this is 2/3. On the other hand, the probability of picking the right door is 1/3. The probability of winning, if one picks the right door and stays put, SP, is 1. So the probability of winning, if one stays put, is winning stays put is right door stays put. So this is all 1, but this is only 1/3. This is 2/3, and wrong door stays put 0. So this is altogether 1/3. So you see, if you switch, the probability is twice as high. So suppose now the set A is, so here we've been thinking of things, events that are discrete, sets of outcome, the outcomes are all discrete, sets of outcomes are discrete, and so we're in sort of the kind of mathematics that children understand. If we then go to the real numbers, then the set of outcomes can be, the outcomes can be labeled by real numbers that vary continuously, and the set A might be the interval around of with delta dx around the point x, and then you can say P of A is P of x dx. So now Bayes' theorem looks like this: probability of x given B is probably B given x times probability of x, and then we have to divide by P of B, and P of B is all the probability of x prime is probability of B given x prime. So that's another I don't know if I should call it a theorem, a lemma, or an identity, or a relation. Anyway, it's a something or other fact, I guess. Now let's look at a pole. And what I'm going to be saying here about poles is actually, it's a simple version of what happens, I think, in the big leagues when these guys, when these professionals do polls. But obviously they ask more than 4 people, but I wanted to keep the numbers simple. So I have 4 people asked if they're going to vote for Nancy Pelosi. 4 people who don't pay attention to American politics. And Nancy Pelosi is the presently Speaker of the House of Representatives, and she's been a member of Congress representing part of San Francisco for many, many years. Anyway, so if the probability that a random voter will vote for her is Y, then the probability that 3 in our sample of 4 will is probability of 3, given that the average probability is Y. Well, there are, you cube Y, the probability of not voting for is 1 minus Y, and there are 4 ways this can happen. This is a term in the binomial distribution, which is just defined so as to be this. So the ideally, I would have already done the binomial distribution, but you guys know about the binomial. Here, let me just switch to the binomial distribution for a second. The binomial distribution is this sort of thing. The probability of success is P on each try. Then in capital N tries, the mean number of successes will be N times P. The probability of failure on each time is each try, of course, is 1 minus P. And the probability of a particular sequence of successes and failures, such as N successes followed by capital N minus little n, Failures is p to the n, q to the big N minus little n. There are capital N factorial divided by little n factorial, big N minus little n factorial, different sequences of n successes and n minus n failures, all with the same probability. So the probability of n successes, n minus n failures, and n trials is this thing, which is the number of such trials, the probability of each. And this is the binomial coefficient. This is the binomial distribution. If you sum, Q, of course, is 1 minus P. And if you do this sum, we saw some time ago that this is just 1 plus P times, or P plus 1 minus P, and it's just 1 raised to the nth power. Anyway, the binomial distribution looks like this. This is for P equal to 0.2, N equal to 125, 250, and 500. And so as you increase the number of tries, the probability of n successes in that many trials starts to look like this as it gets lower and broader. Well, anyway, I think I should just go back to where I was. So let's see if I can go back to where I was. So I don't think I really cleared things up very much there. So let's get back to Nancy Pelosi and the poll. So anyway, you can see just thinking that this should be that. So because we don't know what the prior distribution P of y is, and so so you might be tempted to say, oh, okay, we're going to quit because this is an impossible question. And of course, really it is impossible, but we're talking about probabilities here, not about exact results. So what we do the best we can, and since we don't know what P of y is, we just set it equal to unity on the interval 0 to 1, which of course makes it normalized, which is what we want. So now we use the continuous form of Bayes' theorem, which was this. And our cheap poll, and so the probability of y given 3. Now remember what y is. Y is the probability that a random voter will vote for Pelosi. So it's the probability, by Bayes' theorem, is the probability of 3 given y times the probability of y divided by the probability of 3. But the probability of 3 is an integral over the various y primes from 0 to 1 times the probability, of 3 given y prime. But we're going to set P of y prime equal to 1, so it's just this. This we already computed, it's that, so we stick that there. And we now integrate over it for y prime, so we have that. So we do both. We do the integral in the denominator, divide, and we get this expression. So far, we just have the probability that it's the probability of the probability, it's the probability that y voters out of 4 will vote for her, or that an arbitrary person will vote for her. And so the probability that she'll win the election then, of course, is the integral of that from 1/2 to 1, because if that probability is less than 1/2, she's going to lose. And so we just integrate this and we get 13 over 16. Now, of course, naively, you'd say, well, if 3 people out of 4 voted for her, the chances of her being elected are 3 out of 4. I mean, that's plausible. but it's unmotivated and wrong. The correct answer is 13 out of 16, whereas this is 12 out of 16. I'm going to skip that transitivity one and just go to quantum mechanics for a minute. And the point here is that we've tacitly assumed, you see, classical probability theory tacitly assumes that it's easy to tell whether events are mutually exclusive, and that events that look mutually exclusive really are mutually exclusive. And so in quantum mechanics, that's not true at all. So suppose you've got your classic two-slit experiments where I'm sure you guys have all seen this. So you've got photons coming out, you've got a barrier with two slits, and they're equal slits. And what's the probability of a photon being detected at some point on a screen, some point B? And what you've got here then is opening slit 1 and slit 2. And the photon can go from the laser over here, can go through the slits and get to B. And unless we measure which slit the photon goes through, the two passages are not mutually exclusive. So we can't compute the probability the photon is detected as B as the sum probability going through slit 1 times the probability getting to B, given that it goes through slit 1, plus the probability that it goes through slit 2 times the probability that it gets to point B, given that it's gone through slit 2. And so this is the classical formula, and it's not right. And instead, one has to use a quantum mechanical formula in which B is the, bra B, ket A1, inner product is the amplitude that a photon goes through slit 1 gets to B, and this is the amplitude that a photon that goes through slit 2 gets to B. And then you take the absolute value, and in general, these can be complex. So that's an interesting, well, it's the starting point for doing quantum mechanics. So it's sort of amusing. One can start thinking about quantum mechanics, and when you ask, what is it about quantum mechanics that makes quantum mechanics different? There are at least two fundamental things. One is that two events being mutually exclusive is much more puzzling in quantum mechanics than in classical mechanics. And the second is a mathematical thing, which is essentially that the inner product of eigenstates of x and p is e to the I xp over h bar divided by a square root of 2 pi h bar. I could have just written that as e to the I xp over h bar divided by square root of just Planck's constant. And when I wrote that down, what I'm thinking of is that momentum generates translations, which is why this result holds. So it's the connection between momentum and translations in space, and the Hamilton and energy and translations in time. And these things make quantum mechanics different from classical mechanics. So these are the two things, that mutual exclusivity is puzzling and that momentum generates translations. So let's now go to a whole bunch of definitions in probability theory. I'm going to race through these because they're pretty much obvious. In many games, you have n outcomes with probabilities pj, and the sum of probabilities 1, obviously. The expected value, E square bracket x, of an outcome x is its mean, mu, or average value. So it's the average value of x bar. And it's sometimes called mu. And so it's left bracket, it's written this way, it's written as x bar, and it's literally the values, possible values of x times their probabilities. And it's the expected value is also called the expectation of x, the expectation value of x, which is the worst term possible, the mean value of x, and the average value of x. Dirac, in his book on quantum mechanics, chose the right answer, which is the appropriate term for this is the average value of x, which is what it is. And all these other terms are just pretentious ways of describing it. And this particular one, which is not even correct English, it's because the people who taught Americans quantum mechanics originally were German and didn't speak English very well. And so they used a term that made a lot of sense in German, where in German you can take several nouns and just smash them together and make a freight train of nouns. And that makes perfect sense in German, but it's not done in English. The Lth moment is the average value of x to the L. So it's xj raised to the power L times pj. The Lth central moment is xj minus the average of x raised to the Lth power times p of j. And just obviously, or by definition, mu 0 equals nu 0 equals 1, and nu 1 is 0. Now, an important definition is the variance. It's the second central moment. So it's the average value of x minus the average value of x squared. And if you do this sum and expand this square, you see there's a cross term, and the cross term cancels one of these expressions. So you get the average value of x squared minus the average value of x squared. The standard deviation is just the square root of the variance. If the values of x are distributed continuously according to a probability distribution or a probability density, then you expect to be normalized to unity. Then the average value is, let's fix this. The mean value is this, the Lth moment is that, and the L central moment is this, and the variance is the second central moment, which is the average value of x minus the average value of x squared. Okay, and the standard deviation is the square root of the variance, always. The people who are mathematicians and people who are professional statisticians often use f of x for a probability distribution and capital X for a cumulative probability distribution. So in other words, the statisticians might say f of x is the cumulative probability distribution from minus infinity to the point x, which a physicist might write as the integral of the probability distribution from minus infinity to x of p of x prime dx prime. And then the statistician would say, not p of x prime, f of x prime. Notice that capital F of x is necessarily monotonic because its derivative is just p of x, which of course is positive because it's a probability. Mathematicians and statisticians sometimes call a probability distribution or reserve the term probability distribution for the cumulative one and for the discrete one, and call a continuous probability distribution a probability density function or a PDF. So those are different terms for the same thing. All probability distributions must be normalized, but some have what are called fat tails. In other words, instead of being like this, let me just give in other words, the standard probability distribution, the other way is your standard Gaussian distribution. So this goes down as e to the minus x squared over, I don't know, let's see, sigma, I guess, or 2 sigma, square root of 2 sigma. Anyway, it goes down exponentially. But there are some distributions that occur that'll kind of like this. So they're still normalized. You can still integrate them over the real line or over the, maybe over the line, over the positive real numbers, but they don't decrease exponentially. They decrease at maybe something like 1 over a squared plus x squared, something like that. And these occur in finance, and in fact, things in finance have sometimes remarkably fat tails. And one thing that I read, for example, is that if you look at the Dow Jones Industrial Average of stock market prices of shares over something like 40 years, somebody did this, and don't quote me exactly on this. What I heard or what I read in a New York Times article is that over those 40 years, in each decade, there were only, in other words, if you, suppose you were trying to time the market and you missed 10, you were out of the market 10 days per decade, or on the average 1 day per year, and you picked the wrong days to not be in the market, you would have lost almost all of the appreciation in stock values over the past over those 40 years. I don't remember exactly if it was 40 years or more, but that shows you that what happens is that in fact, the reason why they said 10 days in a decade is that what happens in some years is that you have one rising day after another, until the market goes up enormously over 3 or 4 days and then does nothing for 2 or 3 years. And so it's very dangerous to time the market. People who pretend to time the market are typically telling fibs. All right, let's do as an example, I guess, or let me ask the students to say something maybe in the chat, on the chat box. Do you want me to go through more of this probability theory? For example, right now we're at this point, well, we haven't gotten mean and variance, the next top, binomial distribution, Poisson's distribution, Gaussian distribution. Okay, so there's a yes from a couple of people. All right, let's go to it then. What about Heisenberg's uncertainty principle? Do you want me to do that, or do you already know that? You've seen that 100 times and you don't want me to bore you to death. So Heisenberg's uncertainty principle or not? Quick, I need a quick yes or no from somebody. All right, somebody said yes. Okay. All right, so in quantum mechanics, the absolute value squared of a wave function is the probability distribution of the position x of the particle, and p of x dx is the probability of particles found within dx of x. And the variance, of course, is written this way. It's kind of it's almost as many symbols as that. At least this is clear, whereas this, I always have to look up what the hell this is. The standard deviation is delta x. And anyway, remember, sigma, this is the variance, sigma is the square root of this thing. And we call sigma the uncertainty in the position. And similarly, the square of the uncertainty in momentum is the variance in the momentum. Okay. So suppose we have a Gaussian wave function, looks like this. Note it's normalized. That's why we have this factor here and this factor there. The uncertainties are delta x is a over 2, delta p is h bar over a. Now, when I say delta p is h bar over a, that's because I know that if you take the Fourier transform, if you look at the average value of momentum, that's what you get. And whoops, what happened here? So let me switch maybe to blue. And what's the average value of P? Well, you can see that because this thing is symmetrical, the average value of P is going to be 0. So what's the average value of P squared? Well, the average value of P squared would be psi star, effectively P squared psi dx. I'm doing things in one dimension, okay? And so this would be, this P is Hermitian, so it's basically P on psi star. Psi is real, so I don't need to screw around with this star. So it's P on psi squared dx. And so this is, well, I should not have gotten rid of the star. Let me just put it in an absolute value here. So what we've got then is h bar over I, but we're going to take the absolute value. So d dx psi absolute value squared dx, and d by dx here, squaring it, we get 2 over pi a, we get h bar squared d by dx of, oh hell, what I've left, I guess, is just the exponential. So this is minus 2x over a e to the minus x over a squared, and this whole thing squared integrated dx. And notice x gets squared here, so there is, let's make this a little bit narrower. X is squared here, so there's no problem. And if one does this correctly, what one finds is that this, as I said, average value of P is 0. So this is, so the variance is just the average value of P squared. The uncertainty then is the square root of that. And so you see that this is, the delta P is going to be H bar over A times something. And the something is a square root of the rest of this stuff here. Square root of, I'll just write stuff. And it turns out that that is actually just H bar over A. And so Heisenberg's uncertainty principle then is delta X, delta P. Well, the uncertainty in X is A over 2, which is kind of obvious from this formula that when X is 0, this thing is 1. When X is A, it's 1 over E squared, which is like a 10th. And so X had better not go farther than about A over 2. Anyway, you multiply those two together, you get H bar over A times A over 2, and that's H bar over 2. And this, in fact, is the minimum. It turns out that these Gaussians are the minimum uncertainty states, and they're related to coherent states, actually. If X and Y are two random variables with a joint probability distribution, then the average value of the linear combination is a linear combination of the average values. There's a Jensen inequality here, which is, first of all, what's a convex function? So let me switch maybe to green then. A convex function is one that lies above its tangents. Okay, now let's see if this is convex. Well, here's a tangent. And then here's another tangent. And so you see it is convex. So this is convex. Because it lies above its tangents. And so let's see, Jensen's, the mean value or the average value of a convex function. So in other words, what we have here is f of x is so the average value of f of x is greater than or equal to f of the average value of x. And the reason for that is, here, let's perhaps give an example. Well, I'm cheating with this example because if I take the average value of x here is 0, and the average value of the function is, well, infinity. So this was the worst possible, the most trivial example. Anyway, that's what's meant by this. This is Jensen's theorem. And a concave function is the reverse. It's a function that looks like this. And so it's below its tangents. Here's a tangent. Whoops, not so good. There's another tangent. The function lies below its tangent. So let's see if I can draw this better. All right, that's a little better. And here I'm imagining this goes down like that. So there's so let's see, what do we have here? Log of x is concave. And remember, here's a graph of log of x that looks something like this. It increases slower than any power of x. And so here what we have then is that log of, I'm going to write this as just average value of x is greater than or equal to the average value of log x. So are there some trivial values here? Well, we'd have to cut this off at some distance because both of these quantities here are infinite if we use the whole real line. So what we're thinking of then is sort of a discrete set of x. If you exponentiate both sides of that thing, you get the inequality of arithmetic and geometric means, namely that the arithmetic mean is always greater than the geometric mean. And that's a very general, interesting result. I think here we're assuming all the x's are positive. Let me just write that down. So there are a couple of other definitions that are common. The correlation coefficient or the covariance. This is completely different from general relativity. The covariance of two variables, x and y, that occur with a joint distribution, P of xy, is P of xy, x minus x bar, y minus the average value of y, dx dy. That's the covariance. And so it's the average value of x minus x bar, y minus y bar. And you can show that that's the average value of xy minus the product of the average values. And the variables are said to be independent if P of xy is P of x times P of y. And if that's the case, then the covariance vanishes. Because you can then factor this, you can factor the probability distribution, so you can factor the double integral and you get just the product, and then you get P of x, you get the average value of x times the average value of y, but then you have to subtract that, so you get 0. But the vanishing of the covariance does not guarantee that x and y are independent. So obviously, the variables being independent is an infinite set of statements. P of xy is P of x times P of y. That's for all x and all y, whereas C of xy equals 0. Well, that's also for all x and all y, but it just doesn't imply the independence. The variance of the sum, well, it's the average value of the square of the sum minus the square of the average value of the sum. And if you multiply that out, you get the variance of x and take the square root. The variance of x plus y is the variance of x plus the variance of y plus twice the covariance. And if you put in arbitrary constants a and b, you get an expression that looks like this. Or more generally, for an arbitrary linear combination, you get something that's the obvious term and then a bunch of cross terms involving covariances. And if they're independent, well, then the variance of the sum is just the sum of the variances with appropriate coefficients. Let me just make sure that I've got that j squared exactly right. I'm a little, well, I guess it is exactly, because it does have this aj squared. Well, let me just, something I should check. So the binomial distribution, so to get back to it, it is the basic distribution. So there are three distributions that we've all heard about many times: the binomial distribution, the Poisson distribution and Gauss's distribution. The Poisson and Gauss distributions are different limits of the binomial distribution. So the basic distribution is the binomial distribution. And so what you have is the probability of success is P on each try. You have capital N tries, and so the average number of successes is NP. And the probability of failure on each try is conventionally written as Q, and it's 1 minus P. Okay, now let me quickly ask the students to say something on chat because we are running out of time. We only have about 11 minutes left. What I want to know is, do you want me to jump back to the general relativity chapter and go through in more detail how you get the affine connection from the geodesic equation? So do you want that, or do you want to just read it on your own? So I need a quick, okay, please go back, one person. Anybody else? All right, well, let me go back, and I tell you what, Wednesday and Thursday, I can do some more about probability and statistics. Okay, so let's jump back here then to GR, and where was it here? Stationary action geodesic. So you can do things in terms of the this square root, but it's rather more complicated. You eventually do get you get a formula for the you get the geodesic equation, and then you recognize inside the geodesic equation that you've got the affine connection there. And so that's the formula. But if instead you use a simpler principle of least action without any square root, and in the text I used lambda here, and I was asked, I think last time, what's lambda? And I said it was arbitrary. It's not really arbitrary. It's true that you can multiply tau by any real number, and well, all right, yeah, tau by any real number and it wouldn't matter. That's true, but you can't set lambda equal to tau squared and expect to get the same equation. So let's stick with tau being the proper time. And what I want to do now is to go to the detailed description of this, and it's something like, I think it's problem 20 in the new version. Or was that a homework problem? Let me just make sure. I don't want to do a homework problem in class. That's a homework problem. So no, I can't do this in class. Okay, so so I'm going to then just go back to probability and statistics, binomial theorem. The probability is, so basically what we've got here is that the probability of a particular sequence of successes and failures is P raised to the n power and Q raised to capital N minus little n. By the way, one of the things that I do is I just label things without thinking enough, and I shouldn't have used little n and big N. If one of these could be n, like this could be little n and this one could be k. But using n for two different things is bad notation. And so I should change that. Anyway, what one has is this, but on the other hand, there are so many different ways of doing this because you see there are n factorial different sequences. And if you have, and there are n factorial different ways of arranging the successes and n minus n factorial ways of arranging the failures. So if we divide, we get that there are that many sequences of n successes and that many failures. They all have the same probability. So the probability of n successes, p trials, no, m successes, capital N tries, probability p of success on each try is this thing, which is the binomial distribution. And it's due to Bernoulli, who, by the way, was working there in the 17th century. And the sum of these is automatically 1. And the average number of successes is in the Bernoulli distribution or the binomial distribution is n successes times the probability of n successes. Well, it's this thing here. And now you can see this is a partial derivative with respect to p with q held fixed. And so you differentiate with respect to p and multiply by p, and you then find that it's n, which is what you'd expect. Then what you can show is that the variance of the binomial distribution then is the square root of the average value of this square. And you can show that that's p times 1 minus p times capital N. The standard deviation then is the square root of this. And the ratio of the width, which is the standard deviation to the mean, then looks like this. And it decreases as n increases. So the width is this, but the mean is that. And well, it's not quite so obvious that this is what's happening here, but it's true. Avogadro's number provides a natural example of this. If you have a mole of gas, well, that's Avogadro's number of molecules. And for those who haven't taken chemistry in a long time, a mole of gas is, well, for example, roughly oxygen has atomic number 16. And on the other hand, molecular oxygen then has atomic, well, molecular number 32. And so roughly 32 grams of oxygen have Avogadro's number of molecules, which roughly is 6 times 10 to the 23rd. If you put it in a cubical box, chance of each molecule being in the left half is a half. The number of molecules is huge. The uncertainty in n is 3×10 to the 11th. So the number of molecules in the two halves, the numbers are equal to, and there it's the sigma over average value is 10 to the minus 12, or 1 part in 10 to the 12. So that's why we think of the gas in a box as being equally distributed, both halves of the box. Well, I think this is something you can read if you're interested, especially if you're interested in biophysics, you should read that. Now, the question is, how do you cope with big factorials? And the funny thing about factorials, you know, when you learn them in school, you just write n factorial and you might write down 100 factorial, think of nothing of it. But you put 100 factorial into a computer and it will crash, or it'll give you 0, or it'll give you some crazy number. These numbers increase so rapidly that you need ways of dealing with them if you're trying to do things numerically. And the short answer is to use the log of n factorial. And of course, n factorial and gamma of n differ by n being +1 or -1. And so what computer scientists have done is invent for Fortran a function log _ gamma of x. The C function is L gamma of x. The MATLAB function is gamma ln of x. The Python function is log gamma of x. And they all give the log of gamma of x as being the log of x minus 1 factorial for real x. Presumably, many of them work for complex x. So if you use the MATLAB version, you can compute the binomial probability, even if little n, well, that was big N, wasn't it? So now I switched in reasonable numbers. 10 to the 7th, what one gets is this exponential of these logs. And this then, because you're exponentiating the difference of these logs, you get something that's handy. I should have maybe done that numerically. In fact, well, I don't know if I can't quite so easily do that on the screen, I don't think. Another way to cope with huge factorials, of course, is use Stirling's formula or Ramanujan's correction or Merman's even more accurate approximations. But this is not such a great way of doing things because you see, you still have a huge number here. It's just that you've approximated in an acute way. So this is probably silly now that I think about it, because this does not help. Although, well, maybe it does help because you can sort of cancel the different thing. All right, so maybe this does work. I don't know. The third way, and this is in fact the reason for the Poisson and Gaussian distributions, is to cope with the factorials. And so the idea is that, well, what did Poisson do? He said, well, let's look at the Poisson distribution. Oh my goodness, I'm way out of time. Okay, so we're going to have to stop now, but well, all right, I'll just say what Poisson did. He said, look, let's take the binomial distribution in two limits. One, huge number of tries, capital N, tiny, tiny probability, namely the average number of successes divided by the average number of tries, make that really, really small, but keep Pn constant as little n, average value of n. And then when you do all that, what you get is the Poisson limit of the binomial distribution. And since you've done all these things, the only number left is the average value of n, the average number of successes. And so it's this Poisson distribution. And So this is Poisson distribution, and I'll say more about this Wednesday and Thursday, and also do the Gaussian and do some more of probability and statistics. But if somebody sends me email, I can cover other topics later this week. All right, so we are really out of time. I'm going to end the thing now.